So today we're going to cover sections 5.2, which is about the addition rule for probabilities. And what we're going to do is first we're going to read a couple of definitions, and then we're going to work on a problem that I gave you for assignment the last time. So the first thing is that we're going to learn today about a compound event. A compound event, the definition is on page 216, is an event that is formed by combining two or more events. And there are many kinds of compound events. The ones that we're going to study in this section are events of the form A or B. So we're going to use the OR operator. So what is, for example, the probability that of A or B is going to be the probability that A occurs or B occurs or both occur. So we're going to go back and to understand this definition of a compound event. We're going to work on problem 40 on page 214 that I gave you the last time. So that problem was based on this frequency distribution. So the number of children that some women had. So, for example, 12,000, more than 12,000 women didn't have children at all. And then there are, this is the frequency distribution. Women with one children is just 7,000, women with two children, 11,000, and so on. So, and then we will ask, the first question was, is the probability that a sample woman has two children? And you know that to solve that question, you need to look at this row, number of children 2, then you have 11,290 women, and then you're going to divide that by the total frequency, which is 46,349. So, but that is a single event. Just having two children is a single event. So I have here in my notes how to solve that first part of the problem. So I just wrote for you here the frequency distribution, and I'm just emphasizing that this is a frequency distribution in one variable. So the only variable x is the number of children. So that's the only variable. So as I mentioned before, if you want to know the probability of any event, we're going to use this formula, the frequency of the event divided by the total frequency. So for the first question, what is the probability that a sample woman has two children? Does the probability of x equals 2, or you can write P of x is 2, or P of 2 children, or P of 2, directly only P of 2. So again, it's just the frequency of having two children, which we read from the table from here. Two children, that's the frequency, and that's the total frequency. So we use that information to compute the probability of a sample woman having two children. So that's with a single event. Now, what happens with the second question? The second question is, what is the probability that a sample woman has fewer than 3 children? Fewer than 3 children. Now, this is the case where we're going to have a compound event. So how do you solve this problem? How did you solve this problem? If you did it, the probability of having less than 3 children is equal to the probability of having 0 children plus the probability of having 1 child plus the probability of having 2 children. That's fewer than 3. Fewer than 3 is 0, 1, and 2 children. So less than 3 children can be written as the probability of x less than 3. So in this case, we are combining 3 events. We are combining the event of having no children, having 1 child, or having 2 children. So we need to combine the corresponding frequencies. So you go back and check the frequencies here for 0, 1, and 2 children, and you're going to copy these three values because these three events are equivalent to the compound event of having less than 3 children. So then you just add up those three values, divide by the total frequency, and you're gonna get the probability of that compound event. I'm just writing here for you the definition. A compound event is an event that is formed by combining two or more events. So this is part of section 5.2, which is on page 216, and it's about the addition rule and the rule of components. So if you solved this problem the last time, you knew that you needed to add three frequencies. So this is the addition rule. We are adding probabilities. That is going to be the definition. So in this case, having less than 3 children for that problem is having 0 children plus having 1 child plus having 2 children. So there are 3 events, single events, and combining the 3 events, you have a compound event. So again, the definition, the case that we're going to work in these compound events are the ones that are using the OR operator. The OR operator. The probability of A or B is going to be the probability that A occurs or B occurs or both occur. So in this case, the probability of having less than 3 children is going to be the probability that X equals 0 or X equals 1 or X equals 2. In this case, there is no chance that X is going to have all the three values. So it's just 0 occurs or 1 occurs or 2 occurs. But you cannot say, oh, both of them occur. That's not possible. So you either have 0, 1, or 2 children. So now there is going to be a different kind of frequency distribution. So I'm going to show you now on page 216 a table. So we have table 5.2 here. So now this is a different kind of frequency distribution because in this table, so you can see the description, this table presents the results of a survey in which 1,000 adults were asked whether they favor a law that would provide more government support for higher education. And in addition, each person was asked whether he or she voted in the last election. So we have now two variables. One variable is whether they voted or not in the last election, and the other variable is just how they think about a law that is going to provide more government support for higher education. So now we have two variables. So and these kind of tables with two variables, they receive the name of contingency tables. So they are categorizing people with respect to two variables. Again, whether they are likely to vote and their opinion on the law. So that's a contingency table. So this is going to be now another way to have frequency distribution. So a contingency table is just a frequency distribution in two variables. So I'm just copy that table here, table 5.2, and I'm just describing how how do people are likely to vote. This is going to be one variable, X, and whether they are in favor or against or undecided about a certain law, that is going to be the other variable. So we say that this is a frequency distribution in two variables. So, and I have here describing again those two variables, and we call this a contingency table. So now we're going to work on other problem to see how we're going to apply the addition rule. So the addition rule can be used either by applying a formula or by applying the concept. So let's see, we have here example 5.11. So we're going to use the contingency table that I just showed you. Use the data in table 5.2 and find the probability that a person is likely to vote or favors the law. So this is the kind of a compound event where the first event is the person is likely to vote. Then we have the operator or. It's very important that you see the operator or, and then there is the second event. The person favors the law. So there are two events here. So this is going to be event A, then we have the operator or, and then favors the law is going to be event B. So we have A or B. So the solution, I'm going to show you the solution first by using the concept of just looking at the corresponding frequencies for those events. So again, I just wrote here for you the operator or. The operator or, anytime that you see the operator or, then you're going to need the addition rule. So the addition rule is just, as I mentioned before, you are adding the frequencies that are in favor of each of these two events. So I have here the table. So the person is likely to vote. So likely to vote is the first row. So all these frequencies are for a person which is likely, who is likely to vote. So I'm going to add 372, 262, and 87 here. But also I need to get now the frequencies for the other event favors the law. The frequencies that indicate that the person favors the law are the first column. So, but be careful, you shouldn't add twice uh, this overlapping frequency. So the only value that we are missing to complete the frequencies that are in favor of this compound event is 151. So I'm adding 151 and I'm going to divide by the total frequencies, which is the sum of these six values, which is 1000. So you're gonna get the uh, the result here, 0.872 as the probability that A occurs or B occurs. So now, mathematically speaking, the general addition rule, which is on page 218, is just for any two events A and B. This is the formula that you're going to use. So the probability of the compound event with or operator is going to be the probability of event A plus the probability of event B minus the probability of A and B occurring at the same time. So which is this probability is going to be the overlapping frequency. So when you use this formula, you get the probability of one event is this, the sum of these three. The probability of the other event is going to be the sum of these two. Then you need to subtract the overlapping region. So again, you have the general addition rule in your book also on page 218. So we're going to work now the next problem, example 5.12, and now we're going to use the addition rule. So let's see, it's going to be the same problem, but now we're going to use the formula. So we're going to refer to the same table before, the same contingency table. And now we're going to use the general addition rule to find the probability that a randomly selected person is not likely to vote or is undecided. So now the events are different. And the method that we're going to use is also different because now we're going to use the formula. So that is the problem. Now we are interested in people, in a person not likely to vote or undecided. So you have the or operator. Anytime that you have the or operator means that you're going to use the addition rule. So let's see. The problem is here. So I just wrote the problem for our notes here. So the first thing, the addition the addition rule is written now here. So the probability of not having a person not likely to vote or undecided, so is the probability of A or B. The formula says that we need to compute the probability of A, the probability of B, and the probability of A and B occurring at the same time. So you're going to add up the first two values and then you're going to subtract the third one. So let's find those probabilities independently or individually. So first, the probability of a person not likely to vote. So we're going to need and check the table, our table. So we have our table not likely to vote. Not likely to vote is the second row. So these three frequencies are the ones that are corresponding to a person not likely to vote. So I'm going to add up 151, 103, and 25. So 151, 103, and 25. If you add up these three values and divide by 1,000, you're going to get 279 over 1,000, which is just 0.0279. So that's the probability of event A. Now, the probability of the other event B. So the probability that the person is undecided about the law. So now we need to check the column for undecided people. So this is the column for undecided people. So there are 87 people plus 25 more people. So we're going to add those two values, 87 plus 25 divided by 1,000. And remember, don't forget adding parentheses if you're going to use R or any calculator to enclose your numerator to prevent mistakes. So you get 112 over 1,000. So 0.112 is the probability of event B. Now, when you use the formula, you need to also find whether there is an overlapping region, whether there is the possibility of that the same person might be part of the other of the both events. So, for example, the probability of A and B is that A and B are happening at the same time. Is the intersection of the column and the row. So is the probability that a person is not likely to vote and is undecided. So we check a person that is not likely to vote is this row, and also is undecided. So the only possibility for having a person undecided and not likely to vote is this square or this field in your tables. It's just 25 people that are undecided and also not likely to vote. So that's the intersection region, 25 over 1,000. So it's going to be 0.025. Then we apply just the formula here. So we have the formula on the top, and we're going to copy the formula here. So, and we're going to use the values that we just obtain 0.279 plus 0.112 minus 0.025 equals 0.366. So this is the solution of the problem if you use the formula. If you don't want to use the formula, you just look at the frequency distribution in two variables. So you look at the table and just highlight the two events. So in this case, undecided person and a person not likely to vote, and then just copy the values for the frequencies within this highlighted region without repeating any of those values. So you have only 4 values here, so you just add up all those 4 values, divide by the total frequency, and you're going to get the same result as before. In one case we use the formula, in the other case we use the table and the frequencies, and we did it in a graphical way. Just we highlighted the region of the table that is representing the compound event. In this case, a person not likely to vote or undecided. So that's the solution for this example 5.12. Now we're going to have one more definition for nodes. So we have now, let's see, we have page 221. So on page 221, we have another definition. It's going to be the definition of the complement of A. So this definition is going to be important to simplify just computations when you have a lot of possible events. Sometimes it's better to just find the complement to solve a problem. So if A is any event, the complement of A is the event that A does not occur. The complement of A is denoted as A with a superscript C, like exponent C. And also the important thing is that the probability for the events that are complement to each other is this. So the rule of complements is on the next page. The probability of the complement is just 1 minus the probability of the event. So the probability of the complement of event event A is going to be 1 minus the probability of event A. So, and I just wrote this for you for your notes, so you can check also the notes that I'm posting online, so to see the definition. So you have here complements and also the rule of complements for probabilities. And this rule indicates that the probability of event A plus the probability of its complement is always 1. So we're going to solve one more problem, and then you're going to have some work to do. So we're going to solve example 5.16. Is on page 222. So let me show you the problem first. So we're going to compute a probability by using the rule of complements. So we have the problem here. It says that according to the Wall Street Journal, 40% of cars sold in a recent year were small cars. What is the probability that a randomly chosen car sold in that year is not a small car? So that's problem or example 5.16. So I just have here the notes. So we know that the probability that you have a small car is going to be 0.40, because that's 40% written as a fraction is just 0.40. Then the probability of having a car that is not small is going to be 1 minus the probability that the car is small. So it's just 1 minus 0.40. Then you get 0.60. So now you're going to have some problems to solve now. So I just giving you these problems from section 5.2, exercise set on page 223. So you're going to solve problems 14, 16, 18, 20, and 22. They are very simple problems, so you're going to be able to solve it very fast. And also remember that when the probability of A and B is 0, so the events A and B are mutually exclusive. So you can check that on page 219. So that means that there is no overlapping region between those two events. So it's like, for example, being enrolled in a math statistics class or not being enrolled in statistics class. So you cannot do, or you cannot have a person being enrolled and not enrolled at the same time. So they are. So, for example, someone that believes in UFOs cannot be the same person that doesn't believe in UFOs. So you either believe in UFOs or not, but you cannot have both conditions on the same person. So, and the other two problems that you're going to solve are problems 41 and 42. So I'm going to show you those problems for you. First, 14 through, let me see, you're going to have problems 14. These problems are here. So, and you're going to apply the addition rule. So 14, you are given the probability of A, the probability of B, and the probability of the intersection of both. So you have 14, 16, 18, 20, and 22. So this is just for you to apply the addition rule formula. And then problems 41 and 42 are more like the problems that you're going to have in your quizzes or in your exams. So 41, first you're going to get a contingency table. So take a screenshot or copy the table and copy the questions. So, and then you have another problem 42, another contingency table. So I'm going to give you time to solve those problems and have them ready to submit later once we finish the lecture. So now we're going to talk about the conditional probability and the multiplication rule. So I'm going to go through this section by looking at the definitions first. So we have, for example, the definition of conditional probability on page 226. So you can just read the conditional probability of an event B given an event A is denoted by P of B, then you have a vertical line, then A, and the probability of B given A is the probability that B occurs under the assumption that A occurs. So when you have this notation P, then the parenthesis, then the capital B, the vertical bar, the capital A, you have to say the probability of B given A. So that's a conditional probability. So, and there are formulas to compute the conditional probability. The formula is on page 227. So you have the formula there. The probability of B given A is just the probability that A and B occur at the same time divided by the probability of A. So see if the probability of an event is 0, then this division is undefined. So when the outcomes in the sample space are equally likely, like for example, when you have the same probability for every element, every event in the sample space, then the probability of B given A is going to be the number of outcomes corresponding to the intersection divided by the number of outcomes corresponding to A. In other words, is the frequency of the overlapping event, or when both events happen at the same time, divided by the frequency of event A. Then we have the general multiplication rule. The general multiplication rule is written here in terms of the conditional probability. So the probability of A and B, so it's going to be the probability of A times the probability of B given A. So the multiplication rule is used all the time that you have the AND operator. Remember, when you have the OR operator, you use the addition rule. When you have the AND operator, you use the multiplication rule. So the multiplication rule is written here. So, and you're going to get the same result if you get first the probability of B times the probability of A given B. We are more familiar with the multiplication rule when there is not a conditional probability. So this is the case when you have independent events. So the definition of independence is on page 230. So two events are independent if the occurrence of one does not affect the probability that the other event occurs. So that's when you say that those events are independent. The other option of the other situation is when they are dependent. And when you have independent events, the multiplication rule simplifies and is easier to understand and is more familiar. We are more familiar with that formula. So the probability that A and B happen is going to be the probability of A times the probability of B. But this formula is only applicable when A and B are independent events. And if you have many other events happening at the same time, so for example, the probability of A and B and C and so on happening at the same time is going to be the probability of A times the probability of B times the probability of C and so on. So it's going to be just a generalization of this rule, but again, it only applies if you have events that are independent. So in few words, what is this thing about conditional probability? I'm just writing uh, the, uh, the idea about unconditional probability. So this is what happens when you are working on conditional probability. So the original sample space uh, doesn't change. So our original sample space is unchanged. When you have conditional probability, then after an event happens, then the sample space changes. So that's the way that we're gonna see problems to be solvable. So I'm going to start solving a couple of problems for you to understand better this idea of conditional probability. I'm going to start with problem 517. Problem 517 is on page 225. So let's read the problem. So problem 517 is here. So let's read carefully, because when you are solving problems on probability, it's very important to read carefully, because again, if you have an OR operator, the OR word, then that means addition rule. If you have the AND operator, that means the multiplication rule. If you have the word now given, then it's conditional probability. So let's see. You have four people, Joe, Sam, Elisa, and Maria. They have been elected to the executive committee of their college student government. They must choose a chairperson and a secretary. They decide to write each name on a piece of paper and draw two names at random. The first name drawn will be the chairperson, and the second name drawn will be the secretary. What is the probability that Joe is the secretary? So you're going to have here the sample space. So this is the sample space for this experiment. So the first name in each pair is the chairperson, and the second name is the secretary. So we have all those possibilities. First, that Joe is the chairperson, and the other three people are going to be the secretary. Then you have Sam being the chairperson, and the other three being the secretary, or Elisa being the chairperson, and the other three being the secretary, and finally Maria being the chairperson, and the other three being the secretary. So now let's write the question and try to solve the problem. So we have the election of two people for the Student Government Association. So the sample space is just given on table 5.3, as we just saw. So, and we have a chairperson and secretary. So what is the probability that Joe is the secretary? So we need to check how many times on how many events Joe is going to be ending up being the secretary. So Joe is the secretary here, Joe is the secretary here, and Joe is the secretary here. So there are only 3 cases in which Joe is going to be the secretary. So I'm going to write 3 outcomes. What is the total number of outcomes? We have 12 pairs. So 3 times 4, there are 12 pairs. So there are 12 outcomes. So 3 divided by 12 is going to be equal to 1/4. So there is a 0.25 probability that Joe is going to be a secretary. And this is unconditional probability because we don't need to change, or there is no need to change the sample space. So Joe is the secretary, and that's it. There is no other condition. So that's the reason it's an unconditional probability. So now we're going to work on the next example to understand now conditional probability. So the next example is example 5.18. So in example 5.18, now we're going to suppose that Elisa is the first name selected, so she is the chairperson. Now, what is the probability that Joe is secretary? So if you read carefully, this case is completely different from the previous one. In the previous one, we didn't care who the chairperson would be. We only care about Joe being the secretary. So there were 3 cases where Joe was the secretary. But now we care about the chairperson. We say that Elisa is the first name selected. So that's the first event. Event A is Elisa is the chairperson. So you can see here in the table that there are the cases where Elisa is the chairperson is only these 3 cases. So our sample space is going to change because of that fact. Elisa, and it's a fact or it's an assumption. The important thing is that the event B is going to depend on event A. So Elisa is the chairperson. So this column, this column, this column, they are no longer needed because we know that Elisa is going to be the chairperson. This is my new sample space, only 3 cases. Now we're going to repeat the process. Out of these 3 cases, in how many cases Joy is going to be the secretary? So you're going to see that it's only 1 case out of 3. So that's the answer for this problem. I'm just going to summarize this here. So for your notes, so you're going to see that now what is the probability that Joe is the secretary? Joe is the secretary in example 5.18. So given A is Elisa is a chairperson. B, event B is going to be Joe is the secretary. So what is the probability that Joe is the secretary given that Elisa is the chairperson? So you're going to write P of capital B, vertical bar, capital A, and this is read as the probability of B given A. So the probability of B given A. So the easiest way to solve this problem is you're going to adjust the sample space. So the new sample space, as I mentioned before, when we were looking at the table, this is the new sample space. Elisa being the chairperson and the other 3 people being the secretary. So now the probability of Joy being a secretary is just 1 case over 3 cases. So it's 0.33. So that's example 5.18. And I hope you now understand a little bit about the conditional probability, and that the best way to solve the problem is that change the sample space and then solve the problem if you were working a single event, not a compound event. So now we're going to solve one more problem, and with that we're going to finish this lecture. So the next problem we're going to solve is example 519. So let's see. So problem 519, example 519 is on page 227, and this is the problem. So table 5.5 presents the number of US men and women in millions 25 years old and older who have attained various levels of education in a recent year. So we have a contingency table. Again, we have two variables. One variable is just gender, men, women. The other variable is the level of education. So we have a contingency table very similar to the ones that you're going to have in your quiz and in your exam. So that's the contingency table. So we're going to need to pay attention to this table and then answer 3 questions. So we have this problem. A person is selected at random. So the first question, what is the probability that the person is a man? So this is just unconditional probability because they don't use the word given. They are not talking about two events. So the first question is just unconditional probability, the probability that the person is a man. So we look at the table, the person being a man is just the first row. So we're gonna add up all those values on the first row and we're gonna divide by the total frequency. The total frequency is we need to add up all these values. So if we do that, we're gonna have the solution for problem part A. So let me show you that. So we have here the probability that the person is gonna be a man. So I'm adding the first row and the answer is gonna be just 0.8021. So that's the first answer to the first problem. Now let's check the second question. The second question is, what is the probability that the person is a man with a bachelor degree? So now we have an event, a compound event with one, and also it's a compound event with the and operator, because with means that two events are happening at the same time. So the first event is that the person is a man. The second event is that the person has a bachelor degree. So we have both conditions to occur at the same time. So the best way is just highlight the frequencies that favor both events at the same time. So you're gonna see that a man is the first row. So we look at the first row, but then we need a person with a bachelor degree, which is this column. So now where is the overlapping region? The overlapping region is just this value. 17.5 is the frequency corresponding to a man and to a person with a bachelor degree at the same time. So this is with the operator A and with the operator and. So you have here the solution for part B then. It's just 17.5 divided by 195. So, and then that's the answer, 0.08974. So that's the solution for the second part of the problem. Now the third one, the last question. The last question now is what is the probability that the person has a bachelor degree given that the person is a man? So now it's a different question than the previous one. So now we know that the person is a man. So what is the probability that that person is going to have a bachelor degree? So this is like just reducing the sample space. We're going to change the sample space. So the original sample space is the entire contingency table, but the first event is that the person that you selected is a man. So now you know that you have only men, a man. So the first row is gonna stay and the second row is gonna be removed completely. So you only have now the first row, the second row is no longer needed. So you know that the person is a man. So that's your new sample space. Now, out of that, you want a person that has a bachelor degree. So then you just need to divide this value by the sum of the frequencies corresponding only to the first row, because you know that the person that you selected is a man. So the way that you're going to write this is in the following way. So we have now the last part of computation. So we have what is the probability that the person has a bachelor degree given, this is important, this word given, that the person is a man. So you're going to write this. The person has a bachelor degree given that is a man. So we're going to work a fraction. So as I mentioned before, we're going to reduce the sample space and it's going to be just the first row only, the first row. So again, we're going to find now the probability of having a bachelor degree is going to be 17.5, the only value on the first row, divided by the sum of frequencies corresponding to that first row only. And that is going to be the answer. So I'm not going to assign you more work because you have a lot of work to do with the previous assignment. So the only thing is that I needed to give you this information about the multiplication rule and the conditional probability, because you're going to have problems like this in your exam and in the corresponding quizzes.